Okay, we're going to get started here. Again, my name is Joe Wilker. I'm with Mazak Corporation out of Florence, Kentucky. And I'm going to talk a little bit today about some of the different additive platforms that we have on a lot of our multitasking machines. First of all, I know there's a lot of different technology here on this floor. So I want to clarify the technology that I'm going to be representative here, and that is direct metal depositioning. A lot of people get this confused with powder bed fusion. As you can see, powder bed fusion is obviously a process that starts from the ground level up and builds a geometry, where we're going to basically start off with a substrate of some type of material and build features off that substrate. As you can see in this timeline, 3D powder bed fusion can do exactly high resolution images and geometry in powder bed fusion. Where we're going to do is laser metal deposition. We're going to build to near net shape, because once we're finished, we're going to machine it right afterwards, or in some cases machine it as we're building. Mazak got into the additive multitasking arena in 2014. We started off with our Integrex style machine, and if you're not familiar with our Integrex style machine, it's a multitasking machine that can do turning, milling, gear cutting, grinding, transfer the second spindle, do the second operation, and the gantry taking it out and putting it in a box complete. So the concept with the multitasking machine is do as many processes as you can within one machine, put it in a box and ship it and get paid, right? So adding additive manufacturing to this model just made a lot of sense to us. So what we actually do is we actually change the cladding heads in and out of the magazine, just like we do our cutting tools. So 1 minute I'm subtracting, the next minute I'm adding. In 2015, we actually expanded that Integrex model to be able to do cladding on the face of a part and also on the inclined surfaces for 5-axis capability, as well as OD. As you can see in this slide, this kind of gives you a process of every process that's being done with one machine. You can see that we're doing some turning, we're doing high-speed cladding or fine cladding operations, we're doing the milling features after that cladding operation, along with turning the powder feeder off. Now we have a laser marking system as well. Finishing a part complete. This slide kind of gives you an idea of how long it took us to build this part. The substrate was 316 stainless. The orange features that you see on the slide are all 718 Inconel. You can see the total cycle time was 454 minutes complete from start to finish. So you're probably asking the question is how does that represent conventional process that we're currently used to today in a subtraction world? Where's the payback? So if you figure and you think about, we have to start off with a hunk of Inconel, right? For about $8,000, we're going to have probably a bucket of worn out carbide by the time we're finished milling all this out. And we're finishing the part actually faster, 9 hours and 48 minutes. But where the savings actually is actually in the material cost, starting with that stainless steel substrate and then just adding the features that actually need to be added to the material for wear capability. The potential applications that we see for this application would be mostly near net shape parts that maybe you have a warehouse of spare parts that are no longer valid for your product line anymore. We could possibly bring those spare parts in, maybe mill some features off, add new features to it, and actually make those spare parts valid again for today's society. Also, repair applications. We've already done a lot of repairs on fins and airfoils for both the aircraft and the turbine blade industry. Coating applications we think is a good fix for this as well. A lot of people have asked me what kind of materials can I bond together. Though this is kind of a starting list that we've kind of like put together as far as the different substrates which are across the top, and on the right side is all the powders that can be actually bonded together with one another. Is there more than this? Absolutely. We haven't even touched the surface in this category. Obviously, there's good cladding operations, and there's also bad cladding operations. And these 7 parameters are the parameters that all require them to be adjusted in order to get a good process. If you got too much argon gas coming across and you're cooling the part too quickly, you're going to get cracks and stuff in your weld process. We've actually went through some tests of our own because we wanted to validate this process. So we actually built a couple test pieces. This one particularly is 718 Inconel that basically we machined it down to a test piece. We sent it out to a third party. They came back with the test results within 10% of what we would get at the mill from your tool suppliers. You can see also the perpendicular and parallel grain structures are normal as anything from the mill as well. We took it one step further. It says, like, how's this going to correspond with 2 different types of materials? So we did Inconel and 718 and did the same test. And again, you can see it obviously broke in the stainless steel portion of it, which is where we predicted. It did not break in the bond section. In this slide here, it kind of shows you the bonding process of the 2 materials, and also the hardness of both of the materials. So based off these tests, we feel like this is an extremely valid process for anyone to use in manufacturing for doing additive. And since then, in 2016, we've actually expanded our platforms. The first one is an I200S with additive capability, which uses a coaxial multi-laser system. The VC500 model, which is here on display in our booth, is a 5-axis trunnion tile laser system along with a single laser, 1,000-watt kilowatt laser system. And then the J600, which is a wire arc system. If someone needs to lay a lot of material quickly, we would probably introduce the wire arc system to you on that model. If you look closely at the lineup of these different cladding heads, the first one being a very low volume application. So if you have a very thin substrate that is very sensitive to heat, this would be probably the process you would want to add material to. The middle one is basically the middle volume rate, where we can lay pretty much quite a bit of material, both with a 1mm cladding head, a 3mm cladding head, and we're working on a 6mm cladding head to lay down material very quickly. The wire arc system, again, is a very high volume application, but it also has a lot of heat buildup. So you have to be choosy on what application is going to fit this category. This kind of gives you a clear, I don't know if you can see along the bottom there, it gives you the deposition rate for each one of these processes. So the multi-laser is like 10 cubic centimeters per hour, jumping up to 60 cubic centimeters with a single laser, and then jumping up to 600 cubic meters for wire arc system. It also gives you the dimension of each bead rate as you're pouring down. The other thing that's important about this is the penetration of the weld going into the substrate. The multi-laser doesn't penetrate into the substrate as near as much as the wire arc system does. Reason why the wire arc gets heated up a little bit further. Now, in these different processes, I'm going to have Jason Jones from Hybrid Manufacturing, who is making the cladding heads for Mazak Corporation. He's going to speak a little bit after I'm done here for about 10 minutes to give you a glimpse of where this technology is going in the future. This section here kind of corresponds with some of the applications that I talked about and which process may be suitable best for the different types of cladding processes. Looking again at the multi-laser system, we want a little bit different platform with this design. We actually use a 5-axis gantry system. And the reason we did this is because it gave us the benefit of integrating this to over multiple machine models that we build worldwide. So this actually has a y-axis travel along with a b-axis travel to allow us to do 5-axis cladding applications. This kind of gives you an image of the inside of the machine along with the rotation of axis of the additive. What's really nice about this is if you notice the x-axis stroke on the current milling spindle is limited to how far I can go up in x. But if you look at the Gantry style, I have much more x-axis stroke, so my build process has just increased. In most applications, you're limited on the milling spindle of how big of a part that you can actually make. Now, I think normally on the Intergrex was only about 13 inches. With this design, we can get up to about 26-inch diameter additive. And again, that head is good for both the main spindle or the second spindle applications. Looking at the single laser unit, which is a 1,000 kilowatt lasers currently, we have this on 2 platforms, the Intergrex 400 AM that I mentioned earlier, and also on the VC 500 AM, which is here in our booth. Again, this design is kind of a breakdown of the system we use on this particular model. We're using a RAM instead of a tool change concept. We come down with a RAM about 200 millimeters away from the milling spindle, again allowing us the capability of both additive and subtraction within one machine. And again, this is a full tilt rotor, tilt 5-axis machine. Looking at the wire arc system, this system is mounted on a J-series Variac style machine, which does have a trunnion table as well. Using a wire arc system, we can deposit quite a bit of material very quickly. Just a couple of test samples that we've done already. This is a unique, actually this belongs to a customer. We started off with 4140 and we did a transition to 718 Inconel, which requires 2 powder feeders to mix the blend of powder as you're building the process. So this is actually going to be a test piece. They're going to put it on some kind of rocket and launch it down a runway at 6,000 feet per second, see if the material peels off and what's going to happen at an impact at that fast. This is another piece that we did. This is an actual roll die. So as roll dies wear out, we can actually refurbish them by milling off the die and then re-welding, recladding new material onto it and then remachining it to qualifications. Just another test piece. This is the piece that we're doing here at the Rapid event here. This is just basically stainless on stainless, but we're building this up in about an hour and 20 minutes. We build this up complete and finish machine it, all within one machine. Okay, that's all I have. I'm going to open it up to questions, and then immediately after this, I'm going to turn it over to Jason Jones, and he's going to talk a little bit about where the future of these cladding heads are going to go. Any questions at this current time? Questions?
Any questions?
So is this do you use a powder or wire as your base?
We're using both. We have one version that's a wire fed, and then the other versions are powder fed. Yeah. Anything else? Okay. Jason's going to come up next and talk a little bit about some future
Good afternoon, nice to be with you. Just asked me to talk a little about the future.
I think that's his mic.
Any better?
Yeah.
Much better. Any better? There we go. That's better. Okay. Are you ready? So it's been an honor and privilege to work with Mazak over the last several years developing their hybrid solution. I'd like to tell you a little bit about what we see in the kind of on the horizon, right? This is somewhat aspirational, but beginning to be fulfilled. We're in the smart manufacturing, I don't know if this is the booth, but I hope this will inspire you. The hub, thank you. The smart manufacturing hub. We are here. Well, where's here exactly? Well, I would say we're just on the beginning of this path into really production parts, right? We've had some very notable early adopters, and in our history as an industry prototyping has featured very heavily. In fact, it's driven most of the development over the first 3 decades of what we've done. I was one of the founding members of the standards committee from ASTM that's focused on additive, and we had a very lengthy discussion about what we should call ourselves as an industry. In 2009, when we decided to name ourselves Additive Manufacturing, it was aspirational. There were a few little pockets of true manufacturing, but in general, it was prototyping. So, having started with prototypes, we are now moving into the parts era, right? Production parts. And everybody's been scrambling around going, okay, how are we going to implement what was a prototyping technology and make it productionized? How are we going to get it ready? How are we going to upscale? How are we going to integrate? I'd like to talk especially about integration. So, prototypes to parts. Here we go. The next phase, the smart phase, is smart products, right? So we're on this prototyping to parts to products. Why do I say products instead of parts? Once you have a smart part and it's made of disparate materials and it functions at another level, it really is a system. It's a product. It's no longer just a single monolithic part, which is what this entire room almost has been predicated on, right? We've built the industry to this size and this scale based on building single material parts for the majority. There are some exceptions, okay? But to get to smart products, how do we actually get there? And borrowing from some of the academic work that's very good, University of Nottingham and UTEP, I love this arm as a concept, as an idea of what we could be 3D printing in the very near future, right? And if we were to zoom in onto that fingertip, what would you actually have at that fingertip? Ideally, we'd be printing sensors and multi-material, real true functionality at multiple scales. Well, how are we going to get there? I spent 7 years of my life trying to answer the following question. Which of these processes, okay, so if you're familiar with 3D printing, they're divided up into 7 categories, right? There's 7 general types or categories of 3D printing. Which of those 7 techniques is going to lend itself to multiple scales, multiple materials, and all of the functionality that we want, right? Metals, polymers, conductives, non-conductives, dielectric materials, everything in between. After 7 years, I came up with a very profound answer. Do you know what the answer is? I'll get to that in a minute. Okay, so trying to answer both of these questions simultaneously, that's what I'll do in the next 7 minutes. Okay, this was my answer. The first time I ever came to Rapid as an exhibitor, I wrote this on the pamphlet. Additive manufacturing for CNC and CNC for additive manufacturing. And several people asked me what I meant. And I'd like to try and explain that in the next few minutes. So that's why I'm here to talk about what the next generation of hybrid CNCs brings to additive. Okay, think of the following word in your mind. Isolated. What do you think of? You can tell your neighbor. Isolated. Okay, now I have a new word. What's the first thing that comes to mind when you think of the word segregated? These are important words. These are evocative words, right? Okay, you got in your mind what these 2 words are describing? In my mind, those 2 words describe additive manufacturing. It is isolated, it has grown up isolated from mainstream manufacturing. And even the individual techniques, the 7 families, are used in segregation one from another. To me, these are the 2 fundamental limitations of additive manufacturing. And being here in the Smart Hub, let's talk about moving beyond those limitations, shall we? So, I would almost say additive is literally in its own box and has been almost its entire history until the last several years as we've started to really try to push it into mainstream manufacturing. And how do you do that? Well, you take a mentality where it was always a switch, right? It was competing technology. It was either you're going to machine this part or you're going to print it. And there was nothing in between. And we said, okay, well, let's take two processes that seem as if they're rivals and look more closely at them. Machining, fantastically mature, highly accurate, very repeatable, well productionized. Additive. Additive has some great flexibility. Geometry, materials, it's relatively slow. It's a lot less wasteful, though, than machining. And we said, these aren't really rivals. These are complementary technologies, and they deserve to be together. This sounds like one of those Indian Bollywoods. I'm not going to start dancing, but they do deserve to be together. And we said, let's put these two things together, right? Let's make them work together. And in that way, they can become complementary for a given set of applications. And that's what's really led to this. Let additive build as fast as it possibly can. As long as you get the microstructure that you need and you're defect-free, let it go as quick as it possibly will. And worry about the surface finish afterwards. Or perhaps interleaved, right? Where you can machine it later on. Let each process play on its strengths. So we said, okay, let's take this additive concept that's inside a cage. Let's break it out. So we took directed energy deposition. We distilled the majority of it into a deposition head. And we said, okay, let's put that together with a machine. And this is something like what it looks like. These are all digitally driven techniques, same as 3D printing, right? This is an extension of 3D printing, but it's inside of a machine tool. And so it's a deposition head or multiple deposition heads, and you can do laser marking as Joe's described and adding metal. And as you add metal, you find that the surface finish is not fit for many purposes, right? Close tolerance, mating parts, threads, all those types of things. The majority of metal parts made by 3D printing by any technique require some kind of finishing afterwards. Could be polishing, could be grinding, but very often it's CNC machining. Okay? So you're kind of getting this concept, right? We can mix these two things together. In my mind, that overcomes the first of these limitations, right? The isolated nature of 3D printing no longer has to be isolated. You can co-locate these processes together. Now, returning to the word segregated, almost without exception, each of these 7 families is used within one silo, right? They're not just in their own box, isolated, but they're actually segregated one from another. In that sense, I'd like to compare it to computing before the internet. Computers, some of you may remember, used to be standalone devices, even personal computers, and they were so useful. And then once we got the internet and were really able to connect them and to share, we were able to cross-leverage so many other people's data and strength. It tremendously and profoundly changed our industry, right? Our whole world, our lives. I submit to you that additive manufacturing is on the same verge just as personal computing was before the internet. We're just about to see it grow to its true stature. Okay? So how do we overcome this? Remember my 7-year dilemma, right? This was a PhD, 4 years. This was 3 years as senior research fellow. This was very, very hard-earned knowledge. And I'm about to share it with you right now for free. Okay? Compliments of Mazak, of course. Okay, here we go. So, which of those 7 processes is going to solve your smart products, aspirations? The answer is, there is no one process that will do it all, I promise you. No one process that works at every scale, I love in Joe's presentation where he compares the different types of metal deposition, and it's essentially one order of magnitude jump up each of those 3 different deposition technologies, right? So you get 2 orders of magnitude spread. That's amazing. Go look at any of these processes out here that you sell, that you buy as a 3D printer. You might be able to go an extra 20% faster or maybe even double it. But an order of magnitude, I don't know of any system anywhere that'll actually jump an order of magnitude faster on the fly in a single, in a digital change. That's really impressive. Okay. So, the answer I submit to you to get to smart products is to actually break out of the box, break down the walls, right? Get more of these technologies available in a single setup, in a mainstream manufacturing context. And something profound happened in 2014. Joe mentioned that that's when Mazak and ourselves as Hybrid began to collaborate. The Integrex i400 was the first machine of its kind. At the time, I don't think people realized what it was setting the foundation for. And let me point out to you why I thought it was so important, this moment. It was a really popular item at the exhibition, which was really fun to see. But most importantly, for the first time, on the fly, you could switch between different scales of deposition using different heads. To our awareness, nobody had ever done it like this, right? You couldn't do a push-button changeover and switch out optics and beam and powder, focus and all those types of things. What it was setting the foundation for, though, is really the era where we usher in the ability to use multiple types of not just additive and not just subtractive, but also metrology techniques all in a single setup. This is one of those visions where we say, okay, if you can switch between two different types of heads for directed energy deposition, what else can you put on the end of a tool holder and switch between? And as a glimpse toward the future, this is the vision that I would present. That if you really are going to get to smart products, and you're going to have conductors at very, very, very fine scales with insulators around them, housed in mesoscale and even macro scale packages, you cannot do it with one single deposition technology. And so not only will metals for macro scale monolithic parts require multiple scales, which is achieved through a hybrid approach, you can also switch through different disparate types of technologies and in that way imitate. The only other place I've ever seen this is in biological growth, right? I love my fingernail because it's so different than the skin around it. And then you think about the blood vessels that are inside, and you start to think about all the layers of scale, and pretty soon there is no one process that will do all of that, maybe apart from biological growth. And so just as a little teaser, we've got, for example, in the machine tool world, we're accustomed to cutting metal, right? And when we're done, we look at the surface, but we don't normally look below the surface. And so we said, okay, we had a customer who uses eddy current in a manual way, and they said, can we automate that? And the answer is, sure, why not? So we developed this eddy current head. Here's a little quick video of what it looks like. So in it comes, again, on a tool holder. Once it's in the spindle, drop down, you need a little connection to supply the electrical. Set up whatever parameters you want to be probing at. And now you can look at not only surface, but subsurface. Right? The penetration on this is about a layer thickness of what you've just deposited. You can look for voids. You can see cracks. You can see microscopic cracks. Suddenly you have sensitivity in areas that has not been possible, at least not in process on the machine. One other little teaser for you. Joe's done a great job talking a lot about the different types of metal deposition. What other materials do we want in the same place? Well, my dream is that you will build a metal part. You'll then machine a pocket out of it. You'll then fill that pocket possibly with an insulator, or maybe you'll transition it to a carbon fiber or some other type of composite material. And then you'll be able to embed your electronics, seal it up, finish it, and you will have a smart product. Not a smart part, a smart product. And practicality will mean that an all-in-one machine is the ideal way to understand, develop, and in many cases productionize these smart products. So in that sense, I share with you this vision, where No longer do we have to live in isolation or segregation from an additive or subtractive or metrology perspective, where we really can go make this shift from prototypes and parts all the way to smart products, where these two limitations are completely overcome. And they're replaced with the ability to co-locate or deploy in a single place, on demand, and also integrate all of the different additive technologies that are appropriate to get us all the way to smart products. This is no longer an either-or choice. It never really was, right? This is a spectrum. It's a digital manufacturing spectrum, and you should be in charge of being able to choose when you want to deploy what technology at what scale to reap the maximum benefit for you and your customers. These are the 7 families of additive. May you leverage all of them and in combination. And I thank you for your time today, and I'm happy to take any questions. Or hear any good jokes.
We could use a microphone for questions, please.
Oh, we got another second microphone. We'll share a microphone. How's that?
Okay. I was curious how you address the presence of coolant in that situation.
The presence of coolant. We like coolant. Coolant is our friend. Ironically, putting a laser in a machine tool is like the antithesis of what the machine tool industry has tried to do for the last at least 7 or 8 decades, right? The answer is we turn the coolant on, we use it generously, and we blow it off before we add material the next time around. If it's an organic-based coolant, the laser temperature makes sure it's all gone. We like it dry so your moisture doesn't introduce defects. Okay? So in these machines, yes, there's localized shielding, but the entire chamber is not, you don't vac it down and backfill it with argon like you would a dedicated directed energy deposition system. I got the nod like we're done. Is that what you're saying?
All set.
Our time's cut off. Oh, I have 5 minutes. He says I have 5. Yeah, should we rock, paper, scissors this, or how are we going to? No, I'm just kidding. Thank you very much. If you have more questions, we're happy to answer them up here, and have a great rest of your conference.